In exercise 26 as well, we will study the absolute motion and relative motion. So we have two cars, A and B, have a two-dimensional uniform motion such as VA equal VB equal 10 meter per second. We have two cars, A and B. They both have a constant. They are moving at a constant velocity vector. So the magnitude of this velocity vector is equal to 10 meter per second. They gave us the initial conditions at t equals 0, xa equal y, a equals 0, and xb equal 25 meters, yb equal 0. So this is car A, and car B is this one. The question is, the first one is, determine at t equal 2 seconds the position vectors RA and RB. So in A, they want us to find the absolute position vectors. So these position vectors are observed by an observer that is at rest, that is stationary. So how do we find the position vectors based on the velocity vector? Okay, we know the velocity vector for A and for B. We can deduce RA and RB. So we can start with breaking down the velocity vectors into the I component and the J component. So VA can be written as VA cosine 60 along I plus VA sine 60 along J. Okay, so VA cosine 60 is 5 and VA sine 60 is 8.66. Okay, so we have VA. We found in fact the expression of VA. Okay, this expression is independent of time because we know the magnitude of V A, and we know the angle between V and the horizontal plane. Okay, similarly we can find VB, but please note that for VB, VXB is in the negative direction. It's in the negative direction, so we have to write that VB is equal to minus VB cosine 60, or simply VB cosine 120 along I. This means that VXB is equal to minus 5 along I, and VBX is equal to VB sine 60, okay, or VB sine 120. It's equal to, so therefore we can find that VB is equal to minus 5I plus 8.66J. Now that we know VA and VB, we can deduce RA and RB by simple integration over time. So RA is equal to the integral of VA dt, because VA is equal to dr over dt. VA is equal to 5I plus 8.66J, and RA is equal to the integral of this quantity dt. So please here, when we make the integral, pay attention to adding a constant along I plus a constant along J. The constant along I is xa0 and the constant along J is ya0. And you will obtain RA equal 5TI plus 8.66T along J. Similarly for B, for RB, so RB is equal to the integral of VB dt. We know VB, we have to integrate over time. So the integral of minus 5I dt will give minus 5t plus a constant along I, plus the integral of 8.66J dt is 8.66t plus a constant yb0 along J, and we know xb0 as well as yb0. yb0 is equal to 0 and xb0 is equal to 25, and we can obtain rb and RA as a function of time. We still need to replace t with 2 seconds to find RA and RB at t equal to seconds. Question B, determine at t equal to seconds the position vector RA with respect to B of car A with respect to car B. Okay, they want us to find RA over B. So now we need to find the position vector of A as seen by an observer in car B. Okay, now we have to find the relative position vector. Okay, the position vector of A relative to B. Okay, so we need to apply the rule RA relative to B is equal to RA minus RB, because R absolute is equal to R driving plus R relative. So R relative is equal to R absolute minus R driving. Here, the driving motion is the motion of the car. So this is RB. So we need to subtract RA and RB to obtain RA with respect to B at t equal to seconds. Finally, question C, find the velocity VA over B. So it's the velocity of car A with respect to car B. So we can make the derivation. So VA over B is equal to DRA over B over dt. We found that RA with respect to B is equal to 10t minus 25 along I. We need to derive this quantity. It's equal to 10, and we can deduce that VA over B is a constant. We can also apply as a second method that VA relative to B is equal to VA minus VB. This one is I think shorter. Okay, but in all ways we will obtain that VA over B is equal to 10I.